Welcome to the 4.1 Part 1 notes. Today we're going to use theorems about isosceles and equilateral triangles. Previously, you learned that an isosceles triangle has at least two congruent sides. When an isosceles triangle has exactly two congruent sides, the two congruent sides are called the legs of the isosceles triangle. The included angle formed by the legs of an isosceles triangle is called the vertex angle. The third side that is not congruent to the other legs is called the base of the isosceles triangle. The two angles adjacent to the base and across from the congruent sides are called the base angles, and everything that we just talked about can be summarized in the picture that I'm looking at right here. The top triangle that is adjacent to the two legs is called the vertex angle. The two angles that are adjacent to the base are called the base angles. If two sides of a triangle are congruent, that is, it's an isosceles triangle, then the angles opposite the congruent legs are congruent. So when I say that, opposite of the congruent legs, if I go directly across from the congruent legs to the base angles, they are congruent. So we can say that angle B is congruent to angle C because that AC is congruent to AB. So these two legs being congruent tells us that angle B and angle C must be congruent. This theorem is biconditional, which means that the converse of the theorem is true. So basically you can switch the ifs and thens around. So if, then, the converse of that would be then, if. So you just take whatever the hypothesis of the first theorem would be and make it the conclusion of the second one, and you just switch them around like you see there. So here's the converse of that base angles theorem. If the two base angles, angle B is congruent to angle C, then I know that the sides AB and AC must be congruent because they are across from those congruent base angles. When I say across, you can see the arrows I'm drawing here are across from those angles. The sides are across from those angles. Here's our first example. In triangle DEF, the side DE is congruent to the side DF. What can we conclude? Well, if those sides are congruent, then the angles across from them, angle F and angle E, must be congruent by the base angles theorem. Complete each of the following statements using the triangle diagram below. If HG is congruent to HK, what angles would be congruent? Well, it would be angle G and angle HKG. Can you see that? Those are the angles that are across from the congruent sides. Notice that I had to use three letters for HKG because there are several angles that use K as its vertex. All right. The next one says if KHJ would be this one, is congruent to KJH, which is that one, then what would be true? Well, then the sides across from those angles, KJ and KH, would be congruent. We'll use the triangle below once it shows up here. There it is. Is AB congruent to CB? Explain. Well, we know that this angle DAE is congruent to angle C. So that means the sides across from them in the very large outside triangle must be congruent. That is, AB and BC must be congruent because of the base angles are congruent. Because base angles, angle DAE and angle C are congruent, AB must be congruent to BC. Is angle A congruent to angle DEA? Explain. We'll have to wait, and then I'll explain. I'm sure this probably happens to you in OneNote every once in a while. Sometimes when I make too many pen strokes, it gets angry at me. But we'll be patient. I think I'll just close it and try again. Thanks for your patience. I think we're back now. Is angle A congruent to angle DEA? Explain. So let me erase my markings here. Is the angle DAE congruent to angle A? DEA congruent to angle A. Well, do you see that the sides across from those angles are congruent? So yes, because DE is congruent to DA, then the base angles, angle A and DEA, are congruent. If two sides of an isosceles triangle are congruent and a line bisects the vertex angle of the triangle, then the line is perpendicular to the base. Let's go through that again. If two sides of an isosceles triangle are congruent and a line bisects the vertex angle of the triangle, you can see that CD is bisecting that, then we know that CD has to be perpendicular to the base. So if you have an isosceles triangle where the vertex angle, which again is the angle that is made up of the two congruent sides, is bisected, then that bisector is perpendicular to the base. So we know that CD is perpendicular to AB. And there you have it. It also bisects that bottom segment, that AD should be congruent to DB as well. Using the triangle above, find the value of x. Well, since we can see clearly that ABD and DBC are congruent, that ABD, that tells me that this line DB in the middle must be perpendicular to that base on both sides. And so how many angles, or how many degrees is that angle that's a right angle? You should say 90, right? So we can find out the measure of these bisected angles by saying that 54 plus 90 plus the measure of angle DBA, or ABD, should equal 180. So it should be 144 plus the measure of angle DBA. So therefore, if I subtract 144 from both sides of this equation, I should get, I think, 36 degrees. So that would be the value of x. X would have to be 36 degrees because that's the same measurement as ABD. Hopefully you can see that. Those two angles at the top that are being bisected are both going to be 36 degrees. Suppose that the measure of A was 27 degrees. What is the new value of x? Okay, so instead of 54, we're going to use 27 and do the same calculation. 27 plus 90 plus x would have to equal 180. And so now I have 117 plus x equals 180. Subtract 117 from both sides, and I think that is 63 degrees. All right, here's another fact that we can get from this base angles theorem. And remember, the base angles theorem states that if the two congruent sides of an isosceles triangle are congruent, then the angles across them are also congruent. And so the corollary to that is if a triangle is equilateral, then all of the angles must be congruent. And I'm waiting for my OneNote to catch up with my video here. I'm being impatient here. I'm not going to wait. Thanks for your patience again. Just making sure I can get through this. All right. So what I was saying is that if you know that the sides of the triangle are all congruent, that is, I have an equilateral triangle, then all of the angles must be equal as well. And that is also biconditional. If you know that the triangle is equiangular, then all the sides must be congruent as well. So here's an equilateral triangle PQR. Find the measures of P, Q, and R. Well, we know that since all the sides are congruent, all the angles must be congruent. And so these will all be the same value that I don't know. So if I take x plus x plus x, that should be 180. So that means 3x's are 180. So x would be 60 degrees. So in an equiangular triangle, all of the angles must measure 60 degrees. So the measure of P, oops, forgot the angle symbol, measure of angle P plus the measure of angle Q plus the measure of angle they should all be equal. I'm putting plus signs there. Should all equal 60 degrees. Find ST in the triangle below. Well, you know that all the angles are congruent, so that means all the sides are congruent, so ST would have to equal 5 as well. Can an equilateral triangle have an interior angle measure other than 60? Explain. The answer would be no, since all angle measures of an interior triangle sum to 180 every single time, x, or the angle measure will always be 60. Find the values of x and y. So we have x is here. X plus 1 is this small segment LM. What is that congruent to? All right, that should be congruent to LN. And since LN is a part of this equilateral triangle, we know LN should be 4, and so should y. So I already found y. Y is 4. And x plus 1 has to also equal 4. So then x must be 3. Okay. And I knew this all by looking at the angles. Since the base angles of this kind of obtuse triangle on the bottom were congruent, then I knew those two sides would be congruent. And because of the equal angular triangle here, all these sides should also be 4. So we have a lifeguard's platform here. In this diagram, PS is congruent to QR, and angle QPS is congruent to PQR. What congruence postulate can you use to prove that triangle QPS is congruent to QPR? Well, this is going to make the most sense if I take these two triangles and draw them separately. So the first triangle I'm drawing, QPS, that's the order they wrote down. So triangle QPS would look like this. And again, I have to be patient as I wait for OneNote to catch up here. All right. Having a great day with OneNote so far, but that happens, and so I'm going to keep on keeping on. We'll get through this. I appreciate your patience here while we wait. And so let's go back down to our little lifeguard station. What I was in the middle of doing was highlighting QPS in yellow right here, and I'm going to draw it off on the side, right over here. QPS would look like this. So we have Q, P, and S. We know that SP is congruent. We know that angle QPS up there is congruent. And then we have the other triangle, which is PQR, which I'll color in blue. QPR is in blue, and I'll copy that over on the other side. And we know that this angle, which is angle PQR, is congruent to QPS, and then the side QR is congruent to S. Now notice that they both share the top side, PQ, right? They both share this side, so that would have to be congruent, right? So PQ is congruent to PQ. So what triangle congruence theorem can I use here? Side, angle, side. Explain why PQT is isosceles. So PQT is the overlap in the middle in green here. It's where they all intersect. They have that little point T here. And so PQT would have to be congruent, or have to be isosceles Y. Well, we know that PQ and T, these two angles are already congruent. Okay? Angle 1 and angle 2 would have to be congruent. All right, let's dig into that for a second here. We know that angle QPS is congruent to angle PQR. And the reason that's true is that the measurement QPS would be equal to the measure of PQR. And eventually you can break this down into two smaller angles, Okay, and then they'd end up being by the angle addition postulate. I'm just running out of time here, so I apologize, but you can use the angle addition postulate to prove that angle 1 is congruent to angle 2, and that would tell us that those two sides, PS and, the two sides, PT and TQ, are congruent. I can go over this more in class if you're interested, but there's a way to prove that. All right, to show that triangle PTS is congruent to QTR, well, those two triangles are the smaller ones right here, PTS and QTR. Well, we have a vertical angle right here. We have these two smaller angles that would have to be congruent, and we have this included side. So you'd have to use angle side angle, and I'll go over that in class as well. But thank you for watching. I know I cut this video a little bit short. It went longer than I wanted it to go because of all the OneNote stuff, but thank you for watching.